Thank you. Yeah, my name is Sergio Lopez. I'm a software engineer working in the virtualization team at Red Hat. And here we are going to talk about lightweight virtualization-based solution for containers using LibKrun. So the first question we need to answer is, what is LibKrun itself? And if I had to define LibKrun in a single quote, that will be that LibKrun is a dynamic library that enables other programs to easily gain virtualization-based solution capabilities with the minimum possible footprint. As a fun fact, originally this code said KVM-based instead of virtualization-based, but over the last couple of months, LibKrun has also acquired the ability to create VMs using the hypervisor framework on macOS ARM64, so it's no longer tied strictly to KVM. You can obtain LibKrun by building in-front sources. There are a couple of repositories in the containers organization from GitHub, and there are also some binaries. LibKrun is shipped by OpenSUSE Tumbleweed, so you can install it directly using zipper. There is also a copy repository for Fedora, and there is finally a homebrew tab for macOS on ARM64. So what does LibKrun provide? So provided by the main library, we get some C bindings to interact with the library. We get a virtual machine monitor, a VMM, based on Rust VMM crates and Firecracker. We have some Arch-dependent devices. In fact, the minimum set required to bring up the guest operating system, an integrated VirtualFS server, and a minimal set of Virtual devices, which are Virtual Console, VirtualFS, Virtual Balloon, but only the free page reporting feature, and Virtual VSOC. And provided by LibKrun firmware, we get an interface to access the guest payload that will be injected into the guest memory, and a bundled minimalist Linux kernel has the default payload. So one thing you might be wondering at this point is why provide this feature as a dynamic library. So to illustrate this point, let me tell you what will happen if you had a runtime that and you wanted that runtime to execute a VM using an external virtual machine monitor. So commonly, the first thing the runtime will need to do is to locate the VMM binary, the virtual machine monitor binary, through the file system. And this, in turn, will need to locate its own dependencies also through the file system, probably other dynamic libraries, a kernel image, probably some firmware. There is nothing intrinsically wrong about this, except the complications may come if the runtime intends to switch between contexts, which is something that OCI runtimes tend to do. So, for example, if this runtime switches to a different mount point namespace, it's very likely that the runtime won't be able to locate the virtual machine monitor binaries any longer through the file system, nor any of their dependencies of the virtual machine monitor itself. So this means that the runtime will need to somehow carry on all those binaries through different mount point namespaces, which can be very complicated because the runtime doesn't need to know all those dependencies in the first place. And in any case, it will be it won't be very efficient. So what happens with LibKrun? Well, with LibKrun, the runtime will link it directly against the libraries. So the moment the runtime is executed, the dynamic loader will get those libraries inside the process memory map, and the runtime itself can safely switch between contexts, knowing that will carry on with him all the data and code that it needs to run the VM. So it doesn't need to worry about finding those binaries on the file system. Okay, next topic. Some of you have probably noticed that when I enumerated the virtual devices that are integrated in LibKrun, there was no virtual block, there was no virtual SCSI, not any other kind of device that would provide an emulatable device for the VM. So how are we doing storage without those devices? So basically, the idea is to use VirtualFS to then employ any directory on the host has at the guest root file system. In a very simplified way, we can say that the guest operating system, once the guest operating system wants to access something on the file system, that request will be relayed using Fuse and Virtual MMIO to the integrated VirtualFS server, which is integrated in LibKrun, and the Virtualization server will act on behalf of the guest operating system by using some directory on the host that is acting as the root file system for the guest. And those requests will be resolved through the Virtualization server. The advantages of this mechanism is that you don't need basically any kind of storage management, so you don't need to create these images, nor growing them, nor shrinking them. You don't need to do partitioning on the this image, and nor layer a file system on it. It also it allows to easily share files between the host and the guest out of the box, because that's the way in which it works by default, and it's very friendly to microservice and container workloads. As of these advantages, we can say that the performance is not as good as when using block-based device. The main reason is that the guest cannot rely only on its own cache as it will do with using block-based devices, and will need to communicate more frequently to the host to request file system data. But on the other hand, this is actually good for our memory footprint on the VM, because the lower the cache usage is in the guest, the more memory we have to return to the host to be free and return to further uses. Another disadvantage is that the attack surface is larger than using Virtualization because we need more code, and we need more syscalls. That being said, it's very likely that LibKrun will also integrate support for Virtualization in the near future. The main reason is that Virtualization is better suited for running encrypted workloads. As we've seen just a moment before, the attack surface will be lower with Virtualization because we will need fewer code and fewer syscalls. And also, it's easier and more convenient to run encrypted block devices than running an encrypted file system. That said, if it ever gets integrated, it will probably has an independent flavor of the library instead of a configuration option, mainly because we would like to keep LibKrun as open united as possible, and also to ensure that we are not shipping features that are not going to be used by the runtime. So similarly to what happened with the storage block devices, if they were among the list of Virtualization devices that LibKrun integrates, there were no Virtualization, nor any other kind of device that will provide a virtual network interface for the guests, for the VM. So how are we doing networking without a network interface? We are using a novel technique which is called transparent socket impersonation, TSI, which is implemented in the guest custom kernel provided and bundled in LibKrun firmware. So it doesn't require any kind of changes in the user space application in the guest, which means you can use the same binaries you will use for a conventional container. And basically what happens is that when the user space application requests an AF init socket, what it's actually getting is an AFTSI socket with compatible semantics. And this AFTSI socket has the particularity that it's able to communicate both with the local context inside the VM using an init personality, and with the context outside the VM using a bitsock personality. And all of this in a way that is completely transparent for the user space application. We don't have much time to go into much detail, but if you are curious about this, I did a longer presentation with more slides about TSI on the past DevConf that it should be made. It was recorded and it should be made public in the near future. The advantages of this mechanism of using TSI is that you just require a minimal network configuration, just the DNS. You don't need to configure an IP address or nor any kind of network rules. It also allows LibKrun to act on behalf of the user space application running in the guest without the need of implementing a TCP network stack in the library. So everything happens at a socket level. From the host perspective, all connections appear to come from and go to the LibKrun-enabled runtime and are visible in the network namespace of the runtime's context, which is critical to achieve a certain degree of network transparency we require for something we will talking about in a bit. And there is no need to use network bridges, not virtual interfaces, not IP table rules. And as a result of all of the above, the environment is very friendly to container workloads. to the point that things such as istio sidecars work out of the box without any kind of explicit support for LibKrun. As of these advantages, we can say that TSI requires explicit support for each address family. And at the moment, only AF-INET streams are supported, though it's very likely that AF-INET datagram support is going to arrive very soon. And there is no support for row sockets. Okay, before jumping to the next section, I would like to talk a bit about the container use cases I see for LibKrun. And I mainly see two use cases. One is two main use cases. The first one is to strengthen the isolation boundaries, but this is not about replacing namespace isolation with virtualization isolation, but doing both at the same time, combining the benefits of both of them. Combining virtualization with namespace isolation allows you to use a precise seccomp filter, because we know in advance the syscalls that are going to be executed in that context, because those are the syscalls that are implemented in LibKrun. And it also enables us to use hardware-assisted memory encryption and attestation using technologies such as AMD, SEB, Intel TDX, and others. The second main use case I see for LibKrun on container workloads is the ability to run Linux containers on non-Linux platforms. So, for example, using a simple runtime should enable build that to work natively on non-Linux platforms to the point of even being able to run commands on the working containers. Or we can also do the other way around and use build and slim runtime to run lightweight VMs from OCI images. A lightweight VM is not exactly a container. It's something that sits between a real container and a full VM. And this use case is already implemented in the form of KRunVM. We don't have time to talk much about KRunVM, but if you are curious about it, I did a short demo on the last Podman community meeting, and you can access the recording through the Podman community meeting notes. Okay, so let's jump to the next section, integrating LibKrun in CRUN. We are going to start by seeing a very simplistic overview of how CRUN, or in general any other OCI runtime, does when it's requested to run a container. So basically, it will parse the specification of the container, it will set up the container context, and then it will execute the container's entry point, possibly using XAB or similar syscall. So what happens if we're using a LibKrun-enabled version of CRUN is basically the same thing, except for the third step in which it will check for the run OCI handler annotation. And depending on this value, it will either execute the container's entry point the usual way, using XAB or other similar syscall, or instead, it will create a lightweight VM using LibKrun that will run the container's entry point inside the VM. If what happens is the latter, we'll get something that is closer to this. So basically, on a high-level overview, what we get is the host, then the container context inside the host, which was created by CRUN. Then CRUN plus LibKrun acts as the virtual machine monitor for the VM, then the guest, and running inside the guest the container. Or seeing this from another perspective, we can also say that we have, on one hand, on the left hand, the VM guest running the container inside it, and CRUN plus LibKrun acting as the VM running in the container context. And the key point here is that all the communications in and out from the VM are going through the CRUN plus LibKrun bundle, using Virtual BSOC and Virtual FS as the transport. And since all the communications are going through the CRUN plus LibKrun bundle, and this bundle is running inside the container context, all the restrictions and the constraints applied to the container context are applying directly to the container running in the VM. In other words, what the container running in the VM gets to see is the same thing that the CRUN plus LibKrun bundle gets to see, which is what the container context allows them to see. So in a general sense, we can say that for all the meaningful effects, the container running in the VM is running in the container context. So what happens if instead of having just a single container running in this container context, we have multiple containers running in the same container context? So basically, we will get something like this. Here we have guest A running container A, guest B running container B, and both of them communicating with their own independent CRAN plus LibKrun binary bundle. But those bundles are running in the same common container context, and thus they are able to see the same things, and they are even able to communicate between them using the network and the mount point namespace. So in effect, container A and container B, despite running on different VMs, get to see the same things, and they are even able to communicate between them through the container namespace, the same way it will happen if they were not running inside a VM. So basically what we have here is a pod. It's a pod where each container is running on a different VM, but despite that, it's able to have inter-container communication inside the pod. So summarizing what we have just seen, we all know that by definition, a pod is a group of one or more containers which share network and which share storage and network resources. We've just seen that with CRAN plus LibKrun, each container runs on a different VM, but multiple VMs can run in the same pod's context. We also seen that LibKrun provides a certain degree of transparency for both the mount point and the network namespaces. And all of the above combined implies that containers from the same pod running with LibKrun-based isolation can communicate between them through the mount point and network namespace despite running on different VMs. To make things clear, let's compare the anatomy of a pod running on Kata containers with a pod running on CRAN plus LibKrun. So on the left side, we have a host running Kata containers, that is running a single pod. And here we can see we have a single QEMU instance acting as a VMM. We have a common guest for inside the QEMU in the virtual machine monitor. And inside the guest, we have the container common context that defines the pod and multiple containers running in this context. On the right hand, we have a host running CRAN plus LibKrun. We have the container common context defining the pod directly on the host. And inside this container common context, we have two VMs, each one running a different container. So the main difference here is that on Kata containers, all containers from the same pod will be running on the same VM, while with CRAN plus LibKrun, each container will get a different VM despite being running on the same pod context. And even though they are running on different VMs, they are still able to communicate and see the same things, honoring the context of the container. So Kata containers has some advantage over CRAN plus LibKrun. The main and most significant one is that the Kata containers strategy allows it to support most container workloads, while the CRAN plus LibKrun strategy is restricted to the limitations of both Virtualization-Based and Virtualization-Based plus TSI. Kata containers also has the advantage of being built on mature components such as QEMU, and it also provides a private environment between containers in the same pod, thanks to the fact that all of those containers are running in the same VM. On the other hand, CRAN plus LibKrun has some advantages too. In fact, it provides a simpler environment with fewer moving pieces. It doesn't need to grow or shrink the VM when you are adding more containers or removing containers from the same pod, which is something that personally worries me quite a lot. Basically because growing and shrinking a VM means plugging and hot unplugging the CPU and memory. And those are operations that require the cooperation of the guest operating system, which is something that usually works. But I can imagine that when you have once you have hundreds of containers on each node shutting down and starting up on a daily basis, the chances of something going wrong are quite important, or maybe I'm just a pessimist. This is something that we'll get to know why when these kind of deployments get more widely available. Another CRAN plus LibKrun advantage is that it provides a smaller, it requires less code, which implies a smaller attack surface. And it also has a lower per VM memory footprint, which may come useful if you intend to run many pods with few containers, or you intend to run an environment which you are not going to run any pods and just independent containers. And basically, that's all I have. Thank you for attending the session. And if you have any questions, I will be more than happy to try to answer them.
That's great, Sergio, because we do have a lot of questions. I'm going to let Scott Redmond ask. Scott, do you have a question? And then I will read from the chat. I think I can do that. Scott, are you there? No, you can hold on if you are. I'll just start reading from the chat. So the first question from Eric Ernst was, he's curious if you have a rough number for performance of TSI versus typical IONet configuration by way of latency.
Not yet at this point. I ran some numbers, but they are not really significant at the moment because I didn't have a proper environment to set up. But it's expected that there is going to be a TSI series hitting the Linux kernel mailing list some later this month. It's very likely that I will try to get some actual numbers, comparing them not only against BitIONet, but also against Slurp, which is probably the main contender here.
Okay, great. And Claudio, many people are wondering, how different is LibKrun versus Kata containers? And then as a follow-up, people are wondering about LibKrun, if it should be compared to Firecracker more than Kata containers.
Well, there was a slide, a couple of slides comparing LibKrun with Kata containers. I think that gives some idea of how to compare them, and we can, if there are specific questions, we can try to go a bit deeper about that. About Firecracker, well, Firecracker and LibKrun share a lot of code, in part because both projects are based on RaspBMN, and in part because LibKrun uses a lot of borrows a lot of code from Firecracker. The main difference is that LibKrun is focused on the process isolation use case. So it doesn't provide any other devices that are not strictly required for that use case. And it on purpose tries to remove all code that is not needed for that use case. So because one of the main goals is to achieve the minimum possible footprint in both memory and computing terms.
I see. Okay, next question. Brian was asking, how do the lightweight VMs compare to LXD containers? Now, I think that Giuseppe and Dan answered that with the LXD containers still share the same kernel, but anything else you want to add to that?
No, basically that's the point. If the main difference is that you are here with LibKrun, you are using virtualization-based isolation, which is going to always have some weight, of course, but it also gives you a stronger boundaries if you need them. So the idea is, or the way I see LibKrun to be used in the container context is not for running all your containers using LibKrun-based isolation, but by running some of them, the ones that are carry on the more critical data, or the ones that you are going to be running on a shared computing environment, or maybe a public cloud or something.
Great. So are volume mounts supported with something like VirtIO FS or a network FS?
I'm not sure about what volume mounts are, to be honest. I guess there must be some Kubernetes feature. But if we are talking about volumes in the context of the -B option of Podman, there will be support. Yeah. Okay, in that case, that will be supported by using CRAN will prepare the environment by mounting those volumes inside the root file system, and then you get the directory that has the root file system through Virtualization-Based inside the VM.
Okay. Will LibKrun get integrated into Podman?
Well, I hope so. So the plans are to first get LibKrun in the most popular distributions. We already have hit OpenSUSE, and I expect to be able to hit Fedora soon enough. And then I would like to at least be able to ship CRUN enabled with LibKrun by default, and then add some kind of flag to Podman, maybe --vn or something, that will instruct Podman to tell CRUN that we want to use LibKrun-based solution on the VM, on the container. Sorry, that would be really, really great.
Next question: can I use my own kernel with libkrun?
No, at this moment you need to use the kernel that is shipped with the LibKrun firmware. It's bundled in the LibKrun firmware library, this is not expected to change in the near future, but we'll see.
And what base OS image on libkrun are you evaluating by default for now?
Well, to be honest, I've run a number of OCA images around them. At one point, I took the 10 most popular container images, and I tested them, and they work.
Okay. Wow, we have a lot of questions. Regarding the libkrun versus Kata comparison, can you compare the use cases instead of the technologies? In which scenarios do you expect libkrun to overtake Kata?
Well, this is a complex topic. I think the main point here is that we need to talk about you are willing to pay the cost of virtualization on your containers. And I think in most cases that you are willing to pay that cost is when you are running containers that are carrying on critical information, and you need to have a stronger boundaries between them. That means it will be something closer to trusted and secure enclaves. So that won't be necessarily a strictly speaking conventional containers. And if we are targeting that kind of use case, then we may be able to sacrifice more features. And if we are able to sacrifice features, then LibKrun becomes more attractive because it gives you the virtualization boundaries with fewer code and with a lower footprint.
And for one more question, can I see individual processes running inside of a container on the host, unlike Kata, where I can only see QEMU?
No, at this point, we don't have that feature. It's something that at some point I've considered implementing, having some kind of ability to somehow create placeholders on the host side that would allow the guest, the processes in the guest to be visible outside it. I don't know if it's for the use case of secure containers, if that will really make sense. But it's something that I think it will be interesting to explore in the future.
This was an amazing talk. Thank you so much, Sergio, and enjoy the rest of the conference. Thank you.
Thank you for having me.